Welcome back to my Commodore 64 Games Memories video series. This is where I look at old games and some of the technical details behind them. Today we have the Epyx Fast Load, published by Epyx in 1984, programmed by Scott Nelson. I'm going to be looking at how the fast load code starts, where it is in memory, the disk drive code, and also the communication with the Commodore 64. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Let's have a quick look at the binary file. So this is a program file which just loads the Epyx fast load system. It's actually not part of the cartridge. It's just a little basic sys program with associated machine code. So it looks like there's a little startup message at the beginning, and the start address was 3258 in decimal, so we'll put a breakpoint in decimal on that, and we'll just drop the program file on the emulator. Straight away we can see that, well, value 1 is stored into the border and screen color. That makes the screen and border white, and then it jumps to 838. We can see that this comes from the basic, the jump indirected through 0014 in hex there, basically comes from the basic interpreter. The basic interpreter decodes the sys address and then just jumps to it. It's part of the sys command there. Let's let the code run so we can actually see what it does. So it prints this message. The screen is white with the border color. If we have a look through the graphics maps, text screens, there we go, we can see in the RAM in E000 to FFFF, which is underneath the kernel ROM, the RAM underneath the kernel ROM seems to have a whole bunch of data in there now. Now, the bunch of data that's there in memory is actually a lot larger than what's in the program file. So something is going on there, right? If I attach just a normal D64 disk image with a couple of my games demo program files in there, let's just load the directory, see what happens. And nothing really special happens when the directory is loaded. It just loads it with the screen enabled. But if I load now the first program file on there, game demo 1, just ,8 with a colon after it, we can see that instead of having the screen enabled, the screen disables, and we have this rather much faster load. There's no warp speed involved with the emulator there. That was actually the speed that I would normally expect to see. If I do a hard reset so that it clears the RAM, and then I load game demo 1, ,8 normally with the kernel loader, you can see the speed that it normally loads at with the kernel loader. It's quite a bit slower than the fast load, right? So the fast load code is definitely a lot better. The speed is markedly increased. So let's go back to the Epyx fast load code now, and then let's see how it accomplishes this much faster loading. So the main entry point sets the screen and border color to white. Then it jumps back to 838. It's almost like this screen and border color change was an afterthought after this program file had been created. So after stepping through all of this, we start at 838 now. We're loading what's at 80E with an X index, and then we're JSRing to FFD2. FFD2 is output character on current device. And the current device, because we're coming from BASIC, you would hope that the current device is the screen, right? Here in this documentation, different documentation for the kernel ROM routines, you can see that it's char out. Well, okay, so that's the message that's displayed when the fast load system has been initialized, has been run. So we can see at the moment that there's nothing there in the screen apart from the Commodore 64 Basic V2 message. And then after that initialization has gone on, well, at the start of the initialization, the message is now displayed up at the top of the screen in the debug graphics map there, and also the SC command in the machine code monitor shows this. The screen on the emulated C64 has not had a chance to refresh yet. So this initialization code stops the interrupts, and it's basically loading and storing from the same address index indirected through FB, comma Y, indexed with Y. FB and FC point to E000, which is the start of the kernel ROM. But it's loading from the kernel ROM because the kernel ROM is enabled because we've been called from BASIC. But it copies to RAM underneath the kernel ROM. And on the Commodore 64, if the kernel ROM or the BASIC ROM is mapped in, then a store to that address space will actually store information into the RAM underneath the kernel ROM. You don't need to switch out the kernel ROM to store data into it. So at the moment, using a debug graphics map, we can see that the memory there is just kind of like the normal blank default memory pattern. The Commodore 64's RAM chips typically have this kind of memory initialization pattern. So we're just going to run the code, and then you'll see in the graphics map, as expected, I think, that the data in the kernel will get copied to the RAM underneath the kernel. Now, on the Commodore 64, you can, if you wish, actually copy the kernel to the RAM underneath it and then switch out the kernel, and then the Commodore 64 will keep on executing and act as if the kernel ROM is enabled when it's not. It's just executing the kernel ROM contents from RAM. And you can do that, and it will operate quite happily for a while, unless you start trying to write into the RAM in those memory ranges. But anyway, this initialization code is going to be doing a whole bunch of copies from E000 all the way up until what looks like the end of memory. Now, once it's done that copy, it then goes into this other piece of code, which seems to be copying from 8BF and storing it into, let's just double check this, FB, FC, FD, FE. Yes, it's copying from 8BF, but it's then storing it into F800 in the RAM underneath the kernel ROM. So it's patching a whole bunch of code in the RAM copy now of the kernel code that's located at F800 at least. And there's a little compare there at 872, which seems to go all the way up to FC00. So it's probably, that's the end address, so it's probably copying all of the page at FB00 and then stopping the copy at FC00 by the looks of that. So it's copying from F800 to all the way up to FBFF inclusively. So there, I've got a breakpoint there at 876, and that seems to be after the end of the patch code has been copied over. So we can see there that it's copied all the way up to exclusively the end address at FC00, so FBFF inclusively. The next part of the code seems to be doing a little bit of patching with some certain values at FDD. Well, FDD6 specifically contains the value E5 now instead of what's there currently. And then there seems to be a little bit of extra code there which copies 22 hex bytes long worth of data from 89C to 2C0. 2C0 in RAM is down inside the extended 0-page memory. So I'm just noting these findings down in the debugging notes text file. Of course, as usual, I will be committing this debugging notes text file into source control, into my GitHub repository, and putting a link to this in the video description below. So you can see all of the notes that I've been taking and also follow along with the video if you like. So I'm just noting interesting areas in the code. I'm not going to be going into complete minute detail through all of the code, but I'll be noting down the interesting addresses inside the code as we're moving along. So this code at 2C0, because it's in extended 0-page, if we check this 0-page documentation here, we can see that 2C0 is actually sprite number 11 data area. It's just RAM. We can use it for pretty much anything that we like. In the extended 0-page, by default memory mapping, it's just empty memory. That's why it can actually be used for sprite data if you wish, but normally, generally speaking, this memory is quite free and available if you're just using BASIC and stuff like that. It's not really an issue to use this memory. So the code that's put there is going to be a little bit interesting, I have a feeling. So let's see what else this code does. Let's just put a breakpoint there and continue. This is just after the copy of the code to 2C0 in hex. And now, okay, so the JSR to 8BF. Okay, this just sets up a vector at 330 and 331 in hex to point to the code that was just copied at 2C0. The vector at 330 and 331, if I remember rightly, would be the kernel load vector. Let's just double check that. It's not there, it's in here. 330, There it is, the vector kernel load routine. So with this kernel load routine, the kernel, as it's operating, does make a lot of use of vectors down in extended zero page, interrupts, load routines, all sorts of keyboard handling, run stop key checking, stuff like that. Anyway, so that code there sets up the vector. Okay, so it's also patching those same values, I think, for the code at 2C0. It's patching those values into the RAM copy of the kernel code, and it's patching some certain values into FD4C and FD4D, was it? Yep, okay. There's also, apparently there's some code at 2DB, which was probably copied from the 2C0 code copy. And it's patching the values 2DB there into those two memory addresses, E523 and E528. It's unusual that they're not next to each other, but I guess we can have a look at why in a minute. So we have one entry point which is at 2C0, and then there's another entry point for code at 2D8. Where was that? E523. So there's probably an instruction just before E52. Let's see if we can find E5, probably E522 or E521 if the instruction is right. Let's have a look. Scroll down, scroll down, scroll down. Gone too far. Scroll back up again. E5, a bit further. E5, 2. There we go. Okay. So E522, E523 is load accumulator. Oh, well, that explains why the memory addresses are not adjacent or next to each other. There are two separate load accumulators and then two separate stores. Okay. So it's just patching that code address at 2DB into these two memory addresses. Okay, so it's patching the kernel to call this other little piece of code at 2DB in some certain circumstances. I wonder what those are. It's probably something to do with ensuring that some of the vectors are properly set, perhaps. Routine to determine the keyboard table. Well, I wonder what that's doing. This routine to determine the keyboard table. It might be trying to claim a particular key on the keyboard, so when you press it, it runs code. Perhaps. Who knows? So let's keep on diving in through this code. We haven't actually got to the turbo loading code yet. It's just patching up stuff in the kernel. And then after all of that patching's gone on, look. Well, okay, so this code at 2DB basically switches off the kernel and enables the RAM underneath and then jumps into EB48. Okay, really? Okay. EB48. Well, that's just, okay. So 28D and 28E is it's comparing. Okay, so probably there's some vector restoration code which needs to be made aware that the vectors have changed or something like that, perhaps, maybe, possibly. So there's some vector restoration code somewhere in the kernel, I think, if I remember rightly, that doesn't restore the vectors unless it notices that they're at specific values. So this is just interrupt code which is running, and that's because the interrupts were cleared with the CLI instruction, and then it just RTSs. And then it just, it's just going to go back through and run the rest of the basic code. And then the basic code just returns, and then you get the ready prompt. Okay, then that's fine. So at the moment, there's no drive code being sent during this initialization, it's just copying the kernel into RAM and then patching it. Okay, so let's put a breakpoint at 2C0 and 2DB. See if we can deduce when these things are, or when this replacement code is called. So, but before that, maybe we should save the kernel ROM data, and then we'll save the data that's been copied and patched to underneath the kernel ROM in the RAM space in the same area of memory. And then maybe we can do a binary difference to see what the difference is between the original kernel ROM and then the patched kernel code in RAM. So let's do that. So we'll just use the save command in the machine code monitor here to save the original ROM and then the RAM bank using the same memory address, using the same memory range, address range. Okay, we're just switching between bank ROM and bank RAM in the machine code monitor just to make sure. So then we'll have a little look at those files, I think. But basically now if I do load $8, we can see that actually it's going into the code at 2C0, and that's because the kernel load vector is pointing to the code at 2C0, right? So yeah, that's fine. It's disabling the kernel ROM there with the load with 35 in hex and then storing it into $01. It's saving what is on the accumulator and then restoring it with the PHA and PLA instruction pair there. And then it's just JSR into F86F. F86F is now patched kernel code with the Epyx fast loader code. So just documenting what that little routine there at 2C0 does. And then we'll get back into the code just after I finish typing this. So doing a load at $8 starts executing this replacement code at F86F. And let's see what's at F86F normally in the kernel code. This is actually writing a block from the cassette. So it's actually running some code now. So actually the code has replaced the cassette routines with its own code. So if this code is replacing the RAM copy of the kernel code, if it's replacing that RAM copy of the kernel code over the top of the cassette routines, does that mean that the Epyx fast load for disk kills the cassette routines? Perhaps it does. Perhaps it stops the cassette stuff from working. But basically this kind of like redirection code at 2C0, which is where the load vector points to, just as a little, it's expected. It's after the replacement load routine has been called, it preserves the accumulator, it restores some vector values to what the code expects, and then it banks back in the kernel ROM with load A with 37 and storing it in 1, and then just returns after restoring what the accumulator contains. So let's have a little look at these pieces of code, the original ROM and the replacement code that's sitting in the RAM underneath the kernel ROM. So this is kind of expected. We have a couple of little patched values there near the beginning of the kernel ROM code that's now in RAM, and then we have a whole bunch of changed code. And then we have a few little bytes after the main patched code. But yeah, look at the code differences there. That's a huge amount of code differences. So basically, it looks like this turbo load, the fast load, the Epyx fast load software, it looks like it has obliterated a large proportion of the cassette routines, which is interesting. So just updating the debugging notes text file to reflect those findings. So continuing to debug that replacement code now at F86F, which is the start of the fast load. So it looks like it's loading accumulator with BA in 0 page. BA in 0 page is what, the current device? It looks like it because the accumulator is 8 Yep, there we go. That's the current file first address, which is the device number. So it looks like this code assumes that there's only one disk drive attached, which is drive 8. So it looks like this fast load code actually won't work in its current form with drive 9 or drive 10 or drive 11, just drive 8. So if it equals drive 8, then it goes to F87E. Otherwise, it's probably going to continue at F4AB. So just poking around in memory a little bit there. Okay. Yeah, all right. So this code is going to continue on now at F87E. So yeah, the code is, there's a narrow range of cassette code that has been changed with this fast load stuff, which is kind of expected. So the memory before F800 hasn't really been changed. It's only a memory block from F800 onwards. So comparing it with what's in the kernel ROM by default doesn't show any real differences in the code beforehand, of course. That's kind of what we expect anyway. So stepping through now, loads Y with B7 now in hex, B7 in hex in 0 page. Memory location is probably secondary address. Just remembering to update these debugging notes. So the code checks for drive 8. Yeah, B7 in 0 page is, I think, secondary address. Okay, so it's just storing that in FBE6 just for completeness sake. That's the length of the file name, right? Yeah, of course. So loading indirected BB with the brackets there, comma Y, and then storing it into FBE7. It copies the file name plus the file name length into the RAM underneath the kernel ROM, into this patched code, basically. It checks to see if the file name actually has a length. If not, then in disk world, it will report that a file name is missing if you don't actually have a file name at all. In the tape, you don't need to have a file name, but in disk you do. Anyway, so there's a maximum number of bytes for a file name as well, and we're looking for $, there, which is 24 in the accumulator. So if the file name contains $, that's being passed into this fast load code, then it goes to F87B, which jumps to F4AB. F4AB is outside the area of the patch code from the kernel, and F4AB, let's just double check what that code does. Okay, the unchanged kernel ROM code F4AB, which is copied into RAM, seems to be doing some device checks and stuff like that, device number checks. And it seems to be going into the standard kernel serial loading routines, which is kind of expected because, as we saw from the demonstration earlier, when you're loading the directory, the screen is still enabled. So the screen has not been disabled. There's no fast load code which loads the directory information. So yeah, this is open for serial bus devices, default kernel ROM code, which is in RAM, but it's still doing the same kind of stuff. It just loads serial data. So this code, when you're loading the directory, yeah, it's just continuing the load from using the standard kernel ROM, but in RAM. Serial routines, EDB9 is outside of the patched kernel ROM code, of course. So it's the original kernel ROM code copied into RAM. Yeah, this is just all default kernel code here. So nothing at all to do with the Epyx fast load code. So let's update the debugging notes text file. So it checks for $ in the file name, uses standard load, which is the standard serial routines normally expected to be found in the kernel code. Now we have a disk directory. Let's go ahead and load game demo 1,8. Let's just get rid of the PIG at the end there. And let's debug the code to see what it does now when it's trying to load a file. updating the debugging notes to highlight what we're doing. It goes into the same code that we just looked at just now, except now I'm expecting the compare with $test to fail, obviously, because the file name doesn't have a dollar in it. So here's the compare with $24, which looks for the dollar character. 24 in hex is PETSCII for dollar. There's a little branch on carry clear there, so that's a less than test for Y, comparing with B7, which I think is the file name length. So here is what happens when the dollar file name check fails. In other words, it doesn't find the dollar. It gets to this code here. So F5AF is outside of the area of the kernel ROM code that was copied to RAM. F5AF just handles the messages for loading. So it displays something on the screen for loading messages, which we're not really interested in. But you can see here it says searching for game demo 1. So anyway, what this does now is that it saves onto the stack the vector at 318 and 319, and that's the hardware non-maskable interrupt address. So it looks like this loader is basically claiming the non-maskable interrupt vector and replacing it with, let's have a look, it's pointing it to a specific place in the kernel, and it's pointing it to FEC1, right? So the kernel by default has this set up to point to somewhere else in the kernel, but now it's pointing it to FEC1. FEC1 is just an RTI. So basically the fast loading code is just circumventing whatever the kernel set up as an NMI or whatever the user has set up as a previous NMI by claiming that NMI vector, and it's just pointing it to RTI. So if there is a non-maskable interrupt that comes along, it's just going to RTI straight away. There's also a couple of stores into CIA2, so DD0D, DD06, DD07, DD0F are all locations in CIA2. CIA2 also deals with non-maskable interrupt generation. So it looks like this code is attempting to turn off the non-maskable interrupts. And let's update the debugging notes. Let's just double check those DD0, D0F registers. Yes, this is the timer control register for CIA2 timer B control. It looks like it's just turning it off. Yeah, okay. After it claims 318 and 319, it's pulling those values back off the stack and then restoring them. So actually it's restoring the previous non-maskable interrupt kernel vector there. So after doing all of that non-maskable interrupt timing related stuff, it's now loading what's in D015, storing it in FE, so temporarily, and D015 is the sprite sprite enable control register, so it's turning off all of the sprites. This is not a surprise because if sprites are enabled, it can, or it does, alter the timing of the CPU because the VIC tends to steal a few more cycles. So turning off the sprites is quite a good way of guarding against unexplained cycles being stolen from the CPU. This fast loader, like other fast loaders, is quite timing sensitive. That's why it disables the screen. It looks like it's trying to set up a pointer to FA13 in 0-page memory locations 3 and 4. And it looks like it's also setting up a value of 300 in hex into memory locations 5 and 6. I have a feeling that this is setting up some pointers to probably drive code. That looks like drive code, right? Because it's doing a store to 1800, it's doing a bit test with 1800. So I think that that's drive code that it's setting up to actually send to the drive. Let's step through the code now. Now it's getting to this point in the code at F8EC. After those values are stored into the 0-page registers at 3 to 6. Sending 8 with ED0C is basically sending a listen on the serial bus. So it's telling the drive to start listening to a command. We'll put a breakpoint just after that listen because stepping over the kernel routines doesn't tend to work that well. That's because they do some pushing and pulling onto the stack, I think. Also, there's an interrupt, I think, happening in the middle of that too. Anyway, so the next thing is that it's sending 6F as a data byte with EDB9. So EDB9 sends the secondary address basically to the drive, and this is basically the command channel to the drive, if I remember my drive code specifics correctly. Again, we'll put a breakpoint just after it instead of trying to step over. Now, a load with $90. 90 is the kernel status register for operations. If it's plus, then there's no error. Right, so this is interesting. The code at F901 now starts sending data bytes. So it's sending 4D and then 2D and then 57. And then it's sending the location or the contents of 5 and 6 from 0 page as data bytes. So this is, if I remember my PETSCII codes correctly, 4D, 2D and 57 is M-W. In other words, the command for memory write. Let's just do a memory dump of F901 just to make sure. And there we go. There's the M- and W characters. There's also an M- and E as well. The reason why it's spaced out is because we've got the extra bytes for the opcodes for the load and also the JSR opcodes and the memory address for it. But basically this sends M-W. It's then sending the value in 5 and 6, which is 300 in hex, which is the memory address of 300 in hex in the drive side. It's then sending 1D at F91A there. 1D, I think, is the length of the code it's sending. And then it's sending the bytes of the code or data that it's sending to the drive memory. And it's sending the code in hex 1D long chunks. And this is quite normal. It's quite normal to use multiple M-W commands to send chunks of data to the drive. If we do a memory dump of FA13 on the Commodore 64 side, we can see the memory there, which is being sent to the drive code. After these chunks of data are sent, it then does some pointer arithmetic to increment the pointers, and it checks to see whether or not the pointer is at the end of the data block which is being sent, the larger data block which is being sent to the drive. It sends multiple M-W commands. And so we'll put a breakpoint there at F9 for F because that's the next part of the code. So the screen is currently enabled, but D011 is the VIX screen control register, and ANDing it with EF and then storing it back into D011 will turn off the screen. So the drive, when you're sending M-W commands, you don't need to have the screen disabled. You can have the screen enabled if you like. It's not a problem because you're using the kernel routines and they're quite slow and robust. But after all of the drive code is sent using the M-W command to the drive, then the code is basically turning off the screen, because the next thing that the code wants to do is probably do an M-E, or we'll do the M-E command, and we'll just debug into that in a second. But at the moment, you see, if we have a look at the drive's memory by changing or by doing a memory dump of 8 : which is device 8, as the kernel is sending this information to the drive hasn't really processed the command yet. The drive has received the command, and we can see that. We can see the M-W command, but the drive hasn't really started putting all of the data into memory yet. Let's use the X command just to run ahead now until the breakpoint is hit after the M-W commands are all executed now, or rather all of the M-W commands are all sent by the Commodore 64. However, the drive could still be processing the M-W commands, or the last M-W command. It could still be processing it. The drive doesn't immediately process a command. Actually, there's a little polling mechanism and stuff like that within the drive, which picks up these commands and then executes them at some particular point. is like a job mechanism, and so basically the drive execution of commands can lag behind the Commodore 64 side because they're basically two independent computers. The Commodore 64 talks to the drive side, which is also its own independent computer, across the serial link. Let's have a look what's inside the drive memory now at the point at when it wants to turn off the screen. So the last m-w command there actually contains the file name that we're wanting to load. And if we have a look at 300 in hex, we can see, and 340 in hex on the drive memory now, we can see that the drive memory almost contains everything that the drive code needs, apart from the file name at the end. So the drive is actually still processing the last m-w command. So what the Commodore 64 does is that it's turning off the screen, and the Commodore 64 is then doing a load accumulate with the 8 and then a JSR to ED0C, which is putting the drive into listen mode again. But the drive is still processing the last m-w. So what's going to happen is that this listen command is going to finish until the drive says, hey, I'm listening again. So the drive will then have time to finish processing its m-w command. Or at least that's the theory. I mean, in practice, this is what happens too. But we can test this empirically. We can see the code FA13, which is the drive code that the Commodore 64 side sends. The Commodore 64 has the file name right at the end of this data block. But the drive hasn't completed receiving this last block of data yet from the Commodore 64. So we'll put a breakpoint just after the ED0C, which is the drive listen, the serial device listen. And now, after the serial device has been told to listen, which is the drive, we will check the memory inside the drive side now, and we should see the memory on the drive code actually containing the file name now because it's completed processing the last m-w command. Look at 400, and there we go. There is the game demo file name and the last chunk of drive code and data that has been processed. So by this time, the drive code has completed processing the last m-w, the memory write command. And the Commodore 64 has now acknowledged that the drive is now back into listening mode again. It's not processing its command. It's now sending 4D, 2D, and 4.5, which is m-e, which is memory execute now. And it's sending memory execute with a start address, which is 303 in hex. And then it's unlistening again. And then the drive goes off and that memory executes the memory executes the code, which has been sent at 303 in hex. This drive code is interesting, that it's not just sending drive code, it's sending drive code plus the file name data. So that's good, is that I like this way of doing it because you need to send the drive code anyway to the drive for it to begin to execute the fast loading code. So why not send the file name at the same time as sending the rest of the code block anyway? It's just data that goes into memory. And then the drive code will already have the file name when it wants to start running. So you don't need to send the file name separately. It's a relatively good way of doing it if you are quite sure that you only need to be sending the drive code once at the beginning of a load, or you want to refresh the drive code in memory. If you wanted to have the drive code like resident in the drive's memory, then you might want to have a separate file name sending routine, or you might want to inject the file name into a specific place into the drive's memory and then start executing the code, and then it can just pick up that file name. But it's sending it all as one chunk. It's sending the drive code data and it's also sending the file name data, all just, across multiple chunks of m-w commands, but it's sending it all in one go, if you like. It's not doing two separate sends. The drive code is not resident, it's just sending drive code plus the file name data, which I think is quite nice. It's quite a nice way of ensuring that you have all of the stuff that you need in there. We have a breakpoint at F97D, and that's because after the m-e command, the Commodore 64 is going to, I assume, want to start listening to serial protocol data from the drive code when it's executing. as opposed to the normal drive stuff. Okay, so that's why the Commodore 64 then starts looking at DD00, which is basically a CIA2 port, a serial bus, and also the VIC bank select. But it's not worried about the VIC bank select, it's just looking for the serial bus stuff. And that starts at F97D. Looking at the drive code at 300 in hex, we can see that there's a jump in the first 3 bytes, and then there's the main entry point at 303. So we'll put 2 breakpoints on the drive side, one at 300 and one at 303 in hex, because we want to trap out both instances of those code entry points. So this Commodore 64 code now it's updating the serial port register on CIA2. It's then doing a little delay with load x, dex, and branch not equal back again. So it's doing a delay, and that's probably giving enough time for the drive to start executing its code, the drive code that the Commodore 64 has just sent and just executed with the m-e command. And now at F987, the Commodore 64 seems to be entering the Commodore 64 side of the drive listening code. So let's step into F83F on the Commodore 64, and oh look, it's stopping the interrupts, and it's basically doing what looks obviously like a serial bus or serial port tests and updates. So the Commodore 64 needs to signal to the drive that it's ready to receive information. The Commodore 64 then needs to acknowledge the drive when it says that it's ready, when the drive says that it's ready to start sending information. And then the Commodore 64 needs to receive the information from the drive. So there's a little handshaking protocol here. Commodore 64 says, I'm ready. Drive says, I've acknowledged that you're ready, and I'm also ready. And then the Commodore 64 starts receiving data. So F83F seems to be a general purpose serial data receive function related specifically to this drive code. Don't forget, F83F, even though it is in kernel ROM space, it's not in the ROM, it's in the RAM underneath, and it's part of the patched code that was updated at the beginning when this fast loader code was injected into the Commodore 64's memory, and all of the setup was done right at the beginning. So looking at this code at F854, we can immediately see that there's a load X with 4, and then it does that loop extracting 2 bits at a time for 4 times. Because there are 8 bits in 1 byte, and you're extracting 2 bits at a time, then it's extracting 8 bits in total, and that means it's basically reading or extracting from the data bus, if you like, serial data bus, a full byte from the drive, but it does it 2 bits at a time. In a lot of fast loaders, not all of them, but a lot of fast loaders, they use 2 bits at a time data transfer because it's faster than sending 1 bit at a time. Because if you're sending 2 bits at a time, then you need to do fewer loops through the receiving routine to actually receive all of the bits for a byte. So the Commodore 64 and the drive have to agree that they will start using 2 bits at a time for serial data transfers. It's, you're using more than 1 bit, you're using 2 bits. So the drive code and also the Commodore 64 side of things need to be running compatible code. And because you're using 2 bits for the data transfer, usually the timing between the drive and the Commodore 64 side of the code has to be quite precise, because you're not relying on having a flow control bit and a data bit. You're using both bits, and so there's no real flow or clock or timing control bit in relation to the data bit. You're using both bits for data. So you need to precisely time and synchronize your routines, because there's no timing and there's no clock control bits or anything else like that. So there are lots of different kind of protocols that you can use across a wire for transferring data. And usually you would have, 1 data bit, and then you would have a clock bit somewhere else, or a clock signal. And you would send data, and then you would clock the clock signal to indicate that the data is ready, etc., etc. But in this, by using a 2-bit protocol, you're able to transfer the data a lot quicker, but you have to maintain precise synchronization between the code that's running on the drive and the code that's running on Commodore 64. That's why the screen is switched off, because it's a lot easier to maintain this synchronization. So when the drive is executing its code, it's also jumping into a routine at 300 in hex. So it seems that while the drive is busy going off and doing stuff, the Commodore 64 is basically waiting for the drive to say that it's ready for sending data as well. So we'll dive into that a little bit more. But basically, at this point in the Commodore 64 side, we can see now that once the drive says that it's ready, in acknowledgement to the Commodore 64 saying it's ready to receive data, then at this point at FA4A, you can see the corresponding drive code on the right-hand side. The drive code has already reached the point where it's starting to, or going to start to want to send data. So the data that's in the drive memory at this point, so 600 in hex in the drive memory, actually contains the decoded file data. We can see that there's a sys2061, and then there's a whole bunch of understandable file data. The game demo 1 file on the disk image is basically like a compressed single executable with a sys2061 at the beginning. So the drive code, once it starts executing, it has already found and read the first chunk of the file data. So how did we get there at this point? Because the breakpoint, it actually skipped over quite a lot of drive execution side. So we'll restart the whole process, and we'll try and debug a little bit deeper into what the drive side of things is doing now. Specifically, that's why I'm putting the breakpoints now at 300 and 303 in hex on the drive side. So we'll go back and we'll step back a little bit, and we'll have a look at that in slightly more detail. So let's attach that disk image back again. So there's a little bit of extra code there that was skipped over. So we're just going to go back and have a look. So there we go. We're now debugging specifically the drive code. We're not worried about the Commodore 64 side of things really, because we know that the Commodore 64 is waiting for the drive to say that it's ready to start sending data. So here we go. This is the drive code. So the drive code JSRs to C118. Let's see, what does C118 do in the drive disassembly? Let's step into it. Well, it's just updating 1C00, which is one of the external control registers, VIA registers basically. It's kind of like the equivalent to the CIA in the Commodore 64, but in the drive it's the VIA. And this just turns the LED on. Okay, well that makes sense. You're going to start loading stuff. You want to turn the drive LED on, right? So the drive, first, when it starts executing its code, it turns on the LED. So we'll return now from that routine on the drive side of things. There we go. Let's get the drive 0 page open. Okay, so track and sector for buffer 3, 4, 5. Okay, so it's setting up A, B, and E. So it's setting up the track and sector ready to be read for a specific buffer. Okay. Usually, okay, so these values can be set up to cause the drive to read specific tracks and sectors, but is also setting up a buffer pointer as well. All right, okay. F9. So this code seems to be starting to store information into the drive's buffering mechanism or job code mechanism. So the drive you can tell the drive what to do in terms of job codes, and then it will go and execute those job codes when it can. It services the job queue on a regular basis. Anyway, so F9 there. Okay, so that's probably memory buffer 6, as in 600. The buffer, basically, when it's executing a job code, the drive will use a specific 256 byte chunk of memory for its temporary buffer workspace. So each job uses a different area of memory for its temporary workspace. the job code mechanism, gosh, okay. The job code mechanism inside the drive code tends to jump around all over the place and is a little bit difficult to parse initially and to understand, because it's I would say that it's quite spaghetti-like code. It just jumps around all over the place, initializing memory locations and then executing code and marking jobs as in progress and then complete and stuff like that. The reason why it does this is because the main part of the drive wants to read different tracks and sectors and stuff like that. So you basically can queue up. I want to read this track and sector, that track and sector, this one, and then store it into different buffers. And then you go off and decide how best to execute them. So then the drive, when it has like an interrupt which comes along and then processes jobs on a best effort basis. Okay, it's a flexible system, but it's not a very nice system to try and debug if you're trying to debug drive code. Let's put it like that. Anyway, so the drive code, let's get back to the drive code. So the drive code itself for the fast loader sets track 1, 2 in hex, which is 18 in decimal, 18, and sector 1. That's the beginning of the directory. Okay, so JSRing to 477 in the drive code. What this does is, looking at this, it seems to, again, set up some pointers into, well, not pointers, it initializes values for the track and sector to read into the drive's job code mechanism. It's checking 1C. 1C is disk change, right? 1C is flag for disk change, drive 0. Yes, that's right. So if the disk hasn't changed, then it's okay. But if the disk has changed, you probably want to reread the track and sector, for example. But anyway, so it seems to hop over this, but basically you're resetting. Okay, it's resetting the flag for a disk change, and it's doing B0. B0 looks like a job code. Let's just double check that. Job code B0 is seek. So it's telling the drive to find a specific track and sector. And it's telling the drive to then use or to update the last work buffer, okay, for finding a sector, okay. So just updating the debugging notes text file there, just so that we don't forget what we're looking at. So it doesn't seem to be using the full job code mechanism for the drive. It seems to be updating certain extended 0-page and 0-page memory locations in the drive side to force a specific job code to be executed right now. Don't wait as long as you would normally wait. Just please, hard code some of the job code mechanism to actually execute what the fast loader wants to execute. Not an entirely friendly way of doing it. It kind of circumvents some of the job code queuing mechanism, but okay. And then it's doing a CLI. The CLI is important because the drive's timed interrupt comes along and then processes the job code that basically the drive code is now forcing the drive to want to try and execute. D5A6 in the drive kernel, or drive ROM, the ROM code for the drive, basically, okay, it's checking the drive job has finished. It's checking the job entry in the job code list. It's checking that it's completed before doing the RTS at 4D2. Okay, so while the drive is executing this seek command, the mainline portion of the drive code, which is not running in an interrupt, is then polling to see whether or not the interrupt has completed its work. Okay, fine. This is what can make debugging drive code a little bit difficult, is when it's using this job code mechanism, you have to be aware that it's going to step into an interrupt and then do a whole bunch of stuff which you don't know what it's doing really. I mean, you hope that it's reading or seeking to a specific track or sector, but you're not entirely sure. Anyway, so then after it's done the seek, which was job code B0, is they're now doing job code E0, which is executing. And first, before it executes, it seeks to that track and sector anyway in the drive side of things. So the execute job code will go to that track and sector. Fine, no problem. So the track and sector now is that it's going to start reading the beginning of the directory block. So the fast loader code seems to be doing a seek and then an execute. Okay. Why is it doing an execute? So we'll put a breakpoint on that compare after the job code execute at 4BD returns. Look. So during the execute job, it's hit the breakpoint on the drive side of things at that memory address there at 300 in hex. So that's how that second code entry point at the start of the drive code gets called. And it's jumping into this code here. So it's forcing a value of 6 into 3.1. Okay. So at the moment, the buffer at 600 is empty. There is blank memory there, right? We have the previous command at 200, which is the memory execute command. Okay, that's fine. But the memory in buffer 500, or buffer 5 and buffer 7, they're all empty, look. And buffer 6, which is 600 in hex in the drive side of memory, is also empty. Okay, the beginning of the stack is pretty much empty, apart from the execution stack. The stack pointer is actually not on the drive code side of things. It's actually not at the end of the stack memory. The end of the stack memory is actually used as a temporary buffer as well. But we'll get into that in a bit. But yeah, this seems to force a value of 6 into 3.1 in the 0 page in the drive code. And I think that's the buffer. That's the buffer number to use, which effectively translates to 600 in hex, if I remember rightly. Let's just double check that. Yeah, the buffer pointer for the disk controller. So yes, it's setting the high byte of the buffer address for the drive controller. So the drive controller is basically, with this execute command, is basically being forced to use buffer 600. Why is that? Well, normally when you do a job code track and sector read, the drive might be using a different buffer. So I guess this is forcing the drive to use a specific memory address for its buffer before it actually does the track data read or the sector data read. So this code at MF4D1, this is the drive ROM code, but basically it's finding a particular block of data as the disk is spinning underneath the drive heads. The drive head and the drive is seeing the data as the disk spins underneath the drive head. And so you need to, or the drive code needs to, when it wants to read specific data from a particular sector as it's already on that track, the drive needs to know where it is in the disk spin cycle before it starts. It needs to find the sector data marker before it knows that it can safely read data for that particular sector. So the drive, okay, this is getting into quite technical details, but basically data that's stored on the disk is not just the bytes of the data that is inside the program. It's actually GCR data. So there's this good website which describes the problem with drive electrical mechanics. Is that basically the drive head, when you're reading magnetic flux changes, it can only reliably read, say for example, up to 2 zeros in one go. So computer data can have lots of zeros in a row. So you need to figure out some way of encoding the data on a disk so that you don't have more than two, say for example, 2 zeros of magnetic flux on the disk surface. So you need to expand the data so that you have an arrangement of zeros and ones as magnetic flux changes on the disk, so that you don't have more than 2 zeros stored on the disk. So you need to inject extra ones in there. So this is why GCR was created, was to get around or to solve this problem of being able to reliably read magnetic flux changes from the disk surface. Anyway, what this means is that 256 bytes of data that the computer sees is expanded to more than 256 bytes, and the drive reads in all of this expanded GCR data and has to store it somewhere in memory. So it stores it into buffer 600, and it stores it at the end of the stack as well. So we can see here that the drive code in the ROM is storing into, what is it, 1C A, is that, or something like that at the beginning, or at the end of the stack, and it fills up the rest of the end of the stack memory as well. Then it goes into this whole bunch of huge amount of code. So decoding GCR data, because you're decoding the 5 bits back down into the raw 4 bits of data that the Commodore 64 is expecting to see, the drive needs to spend quite a lot of time and effort in extracting all of the real data from the GCR data. It involves quite a lot of bit shifting and bit twiddling and memory access and all of this kind of stuff. So all of that GCR data decoding is done by the drive, and then it sends the correct data back to the Commodore 64. So that's what F8E0 does, is that it's running all of this GCR data decoding. So because the drive is storing GCR data to buffer 600, and because the real data, once it's decoded, is shorter, we can actually reuse the same buffer. So that's what this fast loader code is doing, is that it's telling the drive to decode back into the same buffer at 600 in hex, the shorter data. So that's okay. That's a little optimization. It means that you don't need to have the GCR buffer floating around in memory, consuming extra memory as you decode it into your real data buffer. Some fast loaders will not use the drive GCR decoding. Some of them will not use the drive expected GCR encoding method. Some fast loaders will use a different GCR data encoding completely. Some fast loaders will not use the expected track and sector markers, for example. But this fast loader, if you recall, I'm attaching a D64 image. Now, D64 images just contain raw data bytes. They don't contain GCR data. So we know for sure that this fast loader doesn't have custom GCR format or anything like that. We know that it's using the drive GCR data decode functions. So we can see here that the drive, as it's decoding data, we can see that it's decoding the GCR data back into expected data. So this data is the start of the disk directory block. We can see game, demo, blah, 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 blah. That's the expected data at the beginning of the disk directory block at track and sector, 18 and 1, track 18, sector 1. So this fast loader just uses standard GCR data. So it's a little bit time consuming for the drive to decode GCR, but that's why the drive ROM has such a huge amount of code in there, is because the code needs to be relatively quite quick to decode all of this GCR data. So after the drive interrupt has finished decoding all of that GCR data, it returns from the interrupt, and then if the drive code in the main line starts executing, and it goes through, and don't forget that the main line of the drive code is now polling to see if the job has completed executing. It just has, because we've just exited that interrupt for processing that job code. So now when the drive code, the mainline code in the drive code side of things, it then checks to see if that job code has completed. And so if we step in, it will now see that the drive code job, or the job code, has completed executing, and then it goes back into the drive fast load code here. The return for the job is 2, and 2 is header block not, it's checking that it's not 2. So 2 is header block not found, but everything is okay because the accumulator contains 1. So that's great. The header block has been found. Everything is okay. So now the drive code, the drive loader code, well, the drive fast loading code can now process the data that's in data buffer 600. So data buffer 600 now on the drive side of things will contain track and sector 18 and 1, which is the beginning of the directory block. So don't forget that the Commodore 64 is still waiting for the drive to acknowledge and to signal it's ready to start sending data. So the Commodore 64 has just executed its memory execute command. And so the drive code is executing. The drive code has already gone off and it's already read the start of the directory. So now the drive code is going to be parsing the directory entries. So data buffer 600 contains the first sector of the disk directory, and it's going to be checking now for the structure of the disk directory block. So just updating my debugging notes text file here, and now we start stepping into this code here. So the Commodore 64 is still doing whatever it's doing. Actually, the Commodore 64 disassembly is not updating right now, but okay. We're just concentrating on the drive code anyway, which is the right-hand disassembly view. So it's starting to parse the directory block. We can see the directory block in the memory dump of 600 there for buffer 600 in the drive code side of things. So there's load with 4D4, and then comparing it with 605. 4D4 is, don't forget, the drive code data which contains the file name that the Commodore 64 has sent. So it's comparing it with 4D4, it's comparing it with 2A is actually the star, right? Is it the star character? Let's just double check that. 2A in Petsky is, scroll down. Yeah, so it's checking for star. Okay, so don't forget file name matching on the drive code. You can use star as like a wildcard for file name matching. So it's comparing with that. But basically, the drive code is looking through the file names in the directory blocks, or the first directory block at the very least, and it's looking to match the file name with what the Commodore 64 is saying that it should try and match with. If the file name match succeeds, then the drive code will eventually get to 3D6 on success. So let's run ahead there until we get to 3D6. There we go. That was just by inspecting the code to see the logical code flow. We don't want to step through all of the individual file name byte checks, right? That would just be a little bit time consuming. So anyway, we now know where in memory in the disk directory block, we now know which file has matched. So the disk directory block doesn't just contain file information, it contains track and sector information. So the track and sector information can then be extracted from that file name entry in the directory block, and then we start reading the track, we're going to start storing the information for the track and sector. So 6 and 7 in 0 page in the drive side of things is the track and sector for buffer 0. Don't forget, in the job code mechanism that the drive likes to use. So it's storing the first track and sector file that matches in 6 and 7. And the file data for that first file name in the directory block entry is track 11 in hex and sector 0, right? So on the disk, files are stored as blocks, individual tracks and sectors. And at the beginning of each block, you have a chain of blocks. So you have track and sector, 2 bytes, and then you have the rest of the byte, the rest of the sector, which is in total 256 bytes long. You have 254 bytes of actual file data. So you have a track and sector byte and then 254 bytes of file data, which is in total is 256 bytes. And this is called like a file chain or a block chain. The last block used for a file has, if I remember rightly, track 0, and then the sector byte is actually the number of bytes that are remaining in the file at the end of the file. I think that's the way around it does it. Anyway, so you have a block chain, so you need to have the ability to read the first block for the file and then extract the next block that you need to read in the chain, and so on and so forth. So then this drive code is now instructing by JSRing to 477 and setting up the track and sector. The drive is basically then being told to read the first block in the file. It's then completing that track and sector read. It's checking to make sure that the read went through okay. If it doesn't go through okay, then it must handle the error, but we're going through the success execution path here. So once the first block in the file chain has been read, yes, it checks everything is okay. Let's update the debugging notes as well so we don't forget. But then it starts. Oh yes, of course, once you've read the first block, you need to remember the track and sector for the next block, of course. But now the drive needs to say that it needs to send the first block of file data back to the C64, of course, because it's just read the first block of file data for the file. So the drive code is just about to start sending this data back to the Commodore 64, and that's happening at 42B. So after getting the next file block in terms of track and sector, we're starting to send the data. So let's step into the code at 42B, 348. Sorry, there we go. So it's doing an EOR with FF, okay, and then a CLI store loadex bit. Okay, good. Right. So the drive seems to be doing, or the drive fast load code seems to be calling 348 to send back a byte to signal to the Commodore 64 that everything is okay or not. Maybe to signal that the file has been found. That would make sense, right? Is that what it's doing? Yeah, perhaps. So the code at 350 there. Okay, so this is doing a 2-bit protocol send in the drive code side of things, yes. However, let's just have a little think. It does seem to be sending a byte to the C64. So there is this code here. The drive needs to signal that it's ready to start sending. Right. So it checks to make sure that the C64 has signaled. So this is what the bit 1800 and then an equal. It's basically saying, Commodore 64, are you ready to send data? And the drive waits for a signal from the C64 first. That makes sense. Because we don't know whether or not for sure the C64 is ready, right? However, the C64 has signaled that it's ready, so the drive then needs to signal that it is ready. Yeah, of course. Where are we? VIA registers, right? We'll just double check that. Yeah, the VIA register is obviously you can see what the VIA registers are doing is that we have data in, data out, clock in, clock out, for example. And there's also the ATN line as well. What is the Commodore 64 side of things doing? So the drive is now doing a little bit of a wait. Now the drive has started sending its 2 bits of data. What is the C64 doing? I don't think the disassembly window for the C64 is actually updating, which is a bit annoying. This is a kind of like an update visual bug. In this version of the Vice machine code monitor is that we're not actually getting the Commodore 64 disassembly view to update as it's executing. Let's go to C:, and then step once, and now it's updated. Okay, we can see that the Commodore 64 side of the code has just completed receiving the data byte from the drive side of the code. So now we have stepped through on the drive fast loader side of things. We've stepped through all of that code, which starts executing the fast load code, which reads the first directory block, parses the directory block, looks for the file name match, and then reads the first block of file data in the file chain. The Commodore 64 then acknowledges this byte which is sent back from the drive, and the drive code, if we do a few more steps, I think the drive code will then go back into the drive code. The drive code on the C64 side the protocol processing on the C64 side of things will then start processing the data bytes from the drive code that's been sent by the drive. So because now the drive code is going off and running its thing, but we're debugging the C64 side. There we go, comparing it with FF. So FF seems to be okay. FF is because it would be track 0. So that's the last. Okay, so that's the last block. That's the case in the drive code. Okay, so that's the C64 side of things. Yeah, the C64 needs to know if it's processing the last data block in the file. If it is, it needs to receive that number of bytes in the last block. Otherwise, the C64 needs to know that it's receiving a full block of bytes from the drive, right? The full 254 bytes of data. So after receiving that first byte from the drive, the C64 knows that it needs to start receiving extra data now from the drive. On the Commodore 64, JSRing to F83F receives a byte from the drive, and it's receiving 2 extra bytes. Normally, for the first 2 bytes of a file on the Commodore 64, the first 2 bytes of the file from the drive, anyway, are normally the original low and high bytes for the address where the file was written from, or where you want the file to load back into. So the first 2 bytes actually should be 1 and 8, because this is a basic program, and basic programs usually, but not always, start at 801 in hex. Loading X with B9. B9, I think, is like the secondary address on the Commodore 64 side of things, and the secondary address is, like the comma 1. If you did load 8,1, then that would be, that would say load the data back into the memory address that is contained at the beginning of the file. If you do load comma 8 without the comma 1, then the secondary address, I think, would be 0, probably. It's certainly not 1. And so the secondary address would, or rather the load address as the first 2 bytes of the file would be ignored, and it would use the values that are in the Commodore 64's 0 page, and that will correspond to 1 and 8, 801 in hex, right, which is the start of the basic program in memory. But yeah, basically basically. The basic program will start loading at the memory address that is set up in 0 page in the Commodore 64. So this drive loading code seems to be trying to implement the original file loading address logic, but I don't think it looks entirely correct, actually, looking at that code. But luckily enough, we are just using load filename, 8, not 8, 1. So we can assume that the basic code, which is a sys statement and then a whole bunch of compressed data after it, is going to load at the same load in the correct place. I might go back and actually check whether or not load filename, 8, 1 actually loads properly in the fast loader, but we'll see. Anyway, so now the Commodore 64 then starts running the rest of the data bytes receive code. Now the Commodore 64, because it knows that it's going to be receiving a whole bunch of bytes from the drive in quick succession, it's running through this code here on the Commodore 64 side, which actually is doing the... okay, so look, it's doing a byte receive 2 bits at a time using the 2-bit protocol for the serial data protocol. But then it's doing a store, if I remember right. We'll go back to the disassembly in a minute. There we go. The store indirect AE, Y. So that's at 4832 there. So it's receiving bytes. The X register is 0. I don't know why it's doing a load A with FB, X. This might just be a timing cycle tweak to match the Commodore 64 side of the code with what the drive code is doing, because loading it or reading the value FB, X, the X as an index into the 0 page memory location, even if it is always 0, incurs an extra cycle execution cost. So it may just be so that this code maintains its synchronization with the drive code. That might be the reason why. So anyway, the drive code is merely sending its 2 bits worth of data for each byte, and it's doing that many times. And the Commodore 64 is merely in synchronization, receiving those bytes of data 2 bits at a time from the drive code, and it's storing them into memory at AE, Y. They're indirected AE, Y, that's what the brackets mean. So once the Commodore 64 has received all of that data, it goes through and it does the same thing again until it reaches the last block in the file. So it's just doing this increment with AF. It's doing an end of data check somewhere in the Commodore 64 side as well. Well, it's updating the store address. Let's put it like that. It's incrementing AF, which AF is the high byte of the indirected memory address for where you're wanting to store this file data. So every time we get into this routine and exit the routine, it's storing a whole bunch of data. So if we go back to the memory debug view, we can see that there. We can see 254 bytes being stored into memory for each chunk. We can see that. And then if we just let it run, then there we go. It's just running through its data now, and it's just running through the whole file data. And then the drive code on the Commodore 64 side of things, the drive code protocol processing code, which processes all of this byte level protocol from the drive, then reaches the end of the file data. Once it gets to the last block, it looks like a slightly special cased code to handle the last block of data. There seems to be the byte from the drive. It does seem to be the last number of bytes. So it's just getting the last number of bytes for the last block, and then it's just storing those bytes into memory, because the last block of the file data might not be aligned to multiples of 254 bytes long, of course, and you don't want to run off over the end of memory for where the file is expected to finish loading to. You don't want to corrupt beyond the end of the expected memory for the file, right? With extra data that shouldn't really be there. Because you might be loading several chunks of data using this fast load. So you want it to behave nicely in terms of not corrupting extra memory when you don't need to. After this last block has been processed, it seems to get into this code here, which then D011 is the VIC control register for the screen, right? So it's turning on the screen, it's re-enabling the screen. We'll just double check that. Yep, VIC2 screen control V register. Okay, so vertical scroll, screen enable, bitmap mode, blah, blah, blah. It's just enabling the screen by twiddling that bit back on again. It's restoring whatever sprites were enabled beforehand from that temporary value that was stored in FE in the 0 page in the C64 memory. It is then turning off a timer, or rather it's making sure that the CIA2 interrupt control is definitely all disabled by the looks of that, by storing 7F into it. It also seems to be acknowledging any interrupts that may occur by reading the register, I think. Okay, so anyway, once that code has completed executing, then it does a CLI. The CLI, because an interrupt was queued, because sometimes interrupts on the Commodore 64 happen because they're timed interrupts. The CLI caused the queued interrupt to occur. That's why it went into interrupt code there. But then after it exited, there's some final cleanup code executing. But basically, AE and AF are the memory addresses for the end of the file that was stored into memory. The kernel load routine has certain expectations for returning values in A, X, and Y, right? So the fast load code, which replaces the kernel load, also needs to satisfy those exit requirements for the load function of putting the correct values into A, X, and Y. So that's just what this code does. It also seems to be restoring values or making sure that correct values are in certain places in the RAM underneath the kernel ROM replacement code. It's then putting 3.7 back into 0.1 because it's exited now the replacement kernel load code, and it's switching the kernel back on again now because the replacement load code has finished executing. We can double check that the kernel load routine, we can double check those exit requirements there for registers. Where is it? It's somewhere here. Yeah, there we go. FFD5, that's the kernel load routine, right? Normally, generally speaking. And so we've got A equals kernel error code, and X and Y is the address of the last byte loaded. So we need to make sure that A, X, and Y are correct. This disassembly and documentation for the kernel, for the C64 kernel, and also the driver ROM code is extremely valuable. It's very useful having all of this information. But yeah, so carry should be clear, indicating that there's no error. The error code doesn't need to be 0, but I guess you can say that it's equal to 0. And then X and Y also need to be set up. So yeah, this fast load replacement seems to be trying to satisfy the register exit conditions for the kernel ROM routine. And then the code then just goes through and then exits back into the kernel stuff and then back into the basic parser, the basic command line parser, because the load command is obviously parsed by basic. And then the code has loaded, and then there you go. It's running. And then this is just, game demo 1, which was one of the game demos that was just on that D64 disk image. I just wanted to use a different emulator now because the Vice emulator and its machine code monitor had that really annoying disconnect between the instruction and cycle timing on the drive code side of things with respect to the Commodore 64 side of things, right? The Commodore 64 window wasn't updating. So I'm going to be using this emulator, which is HOX, and it has much better cycle accuracy or cycle accurate debugging capability compared to Vice and its machine code monitor. So we have the fast load system already loaded in HOX, so we'll just enter into the monitor now, and we need to start setting some breakpoints, right, for the interesting areas in the code that we really want to have a look at, which is just basically the byte receive code on the Commodore 64 side, synchronized with the drive byte sending code on the drive side of things. So we need to set a breakpoint at 2C0 so we can easily step into this. 2C0 was that code that was stored into the spare sprite, 11 data area in memory in an extended 0 page. So there we go. Now we're trying to load that game demo 1 file. We can step into the replacement kernel ROM code now. This is a cycle step. Each instruction can take 2, 3, 4, 5, 6 cycles. Or we can step with the instructions. And we can see now that as the Commodore 64 code is executing, the drive side of things we can also see is updating and executing at the same time. So we need to find the place in the replacement code now which was starting to receive data from the drive. Okay, so we'll put a breakpoint there at F97D, I think, and we'll put another breakpoint there at F989, which is basically the first byte receive code, right? So we'll see what the drive is executing at these breakpoints when C64 is executing stuff. So we have this little delay loop, right? And we can see that this delay loop, we can see on the right hand side that the drive code is still running code and it's wrong, right? So if we continue executing until the Commodore 64 is ready to start receiving data from the drive, we can see that the drive is just finishing an RTS for job code processing on the drive code on the right hand side of things. And then we can see as the Commodore 64 is just about ready to start receiving the first byte, the drive code on the right hand side has now started executing its code from RAM. We can see that it's at 4CD in hex. So on the left hand side, the Commodore 64 is signaling and waiting for a signal back from the drive. Okay. On the right hand side, the drive code is polling its job code completion routine at D5A6. So on the right hand side, the drive on the right hand side is probably trying to read track and sector, a specific block on the drive, on the disk. And on the left, the Commodore 64 is still waiting for the drive to say, hey, I'm ready to start sending data. So we can put a breakpoint to after the drive, hey, I'm ready, wait, on the Commodore 64 side of things completes. And now we can see that the drive code on the right hand side has just signaled it's ready to start sending. There it is. And the C64 side has just acknowledged the drive sending the signal to the C64. And now the drive is going to be doing this bit instruction and branch on not equal loop, which is waiting for the C64 to signal. And now the drive and the C64 are in synchronization. So if you notice, the C64 has this little short delay loop for 8 iterations around that loop, right? Maybe 8. And the drive code on the right hand side is just at this point just started sending the first 2 bits all in one go. So it sends 2 bits with one store instruction. And the C64 has just completed its little delay loop, and the C64 is just about to start reading in one go those 2 bits from the drive. On the right hand side, on the drive code itself is in the process of assembling the next 2 bits to send, but it hasn't sent them yet. The C64 on the left has just read those 2 bits. So the drive code on the right is assembling 2 bits and sending them. The C64 is reading those 2 bits and then disassembling them, because the 2 bits need to be extracted and then stored somewhere ready for the next 2 bits to be read on the Commodore 64 side of things. So this cycle and instruction level accurate debugging in the HOX emulator is much better for when you're trying to debug and precisely time the debugging of drive to Commodore 64 communication protocol issues. Okay, so we can see the drive code is precisely timed to match with the Commodore 64 side of things. And basically, I much prefer the debugger for the cycle and instruction level accurate timing that it can use. But conversely, the machine code monitor on the Vice emulator is a lot more user-friendly, and it has a lot more commands in terms of what to wait for and where to put breakpoints and stuff like that. So I wish I wish the monitor in Vice was as cycle accurate as the monitor in HOX. Or I wish the monitor in HOX had all of the commands that were available in Vice. Vice versa, it would be great. But anyway, yeah, this is the HOX emulator. I don't use it very often, but when I do use it, I tend to only use the HOX monitor and debugger for drive code timing debugging like this. Occasionally, I will use HOX for debugging really difficult to debug VIC chip interactions as well, but the more recent versions of Vice have actually improved their emulation capability with respect to really unusual VIC chip interactions. So I tend to use HOX less now for that. It's just mostly for cycle level accurate drive code debugging. So I think we'll leave this video there. It already contains quite a lot of information. I would like to, as always, thank my supporters for their super thanks and donations to this channel. You are the precisely timed code to my 2-bit protocol. Thank you very much for watching. Take care. Have a great day, evening, or night, wherever you are.